morning. Sorry I bailed on y'all Wednesday. You wouldn't have wanted me here, let me tell you that. um, I'm going to pass around the attendance sheet. Some of you have emailed me the proof that you went to that trailer over there at MG Studios, or MG Warehouse. If you have proof that you went so you can get your extra credit, show it to me today. And then I'll mark it on here and then show it to me as it goes around. Did everyone in here take the exam? I wanted you to have taken it by today. Okay, well, I'm going to push on, so you need to take it today because we have another one next Monday. So, is there any questions on that? Because I wanted it done by today because I put that in the announcement, and I think I even said it before I left that it was a take-home exam, and all we were going to do last Wednesday was a review. So, and then Monday, a week from today, we will not have class because I have a commitment, but then I've arranged that'll be a take-home exam, so that's instead of the class. So today and Wednesday we'll cover chapters 11 and 12, and then you'll take an exam on that, and then we'll meet again the next Wednesday. Does that make understood? Everybody clear? Okay. So go ahead and get that other one out of the way so you can focus. Yes? Yeah? Do you have proof? Well, I asked y'all to bring me something. I wanted y'all to bring something, take a picture, or they had materials there because I went.
Yeah.
So, you didn't bring anything?
I went right as he was closing.
Did you bring anything?
He didn't have anything.
I got that.
All I did was sign up.
Yeah.
Said to put his email and phone number and stuff. So I did sign up for whatever he was offering.
But y'all don't know how to contact him.
I think I got his card and I'm not sure.
Well, you might. That would be proof.
There's the website.
Yeah.
I'm gonna see if he sent me an email.
Okay.
Because I went literally right as he was closing.
Because those that win, I'm giving 10 points.
I got there on 2.
Well, I'm not saying, if I'm making everybody show me proof, I can't just say, oh yeah, I believe you, Thomas. Go for it. So we can either try to contact him. If you have his card, just have him send a quick email saying, yeah, you were there or you signed in. That would be great. So just try to take care of that. Any other questions before I get started? Nope. Okay. I don't know how to broadcast to your screens. They've put a new software on here, and I can't find it. It's called Insight, but I can't turn it on, and the old way doesn't work. So you're going to have to look up here. So I'm not sure. Let me look one more time, but it should be just like right there, and it's not. Oh, maybe that's it right there. I wasn't looking for the owl. Hold on. Let me see if this works. Show. Teacher's full screen. Hey, y'all see my screen? Okay, good. You figured it out? Remind me, it's the owl.
Yeah, exactly.
Can you drag it over? That's crazy. Let me see. Where was that? Blank screen? show on, is it on one screen now?
It's on one screen.
Okay.
You can drag it.
Now you can see that? Okay. And I am recording, I think. Let me check that. Looks like it. Okay. All right. So we're going to talk about steel. I know I said I probably wouldn't do a field trip, but I am going to try to squeeze one in because I think they're fun. So I will keep y'all posted on that. It may not be for till November because I think I have to give them 2 weeks notice. But I'm going to try to get y'all a field trip. So anyway, but on to steel construction. I'm just going to go through the slides that are already been posted on Canvas, and then I have some worksheets we're going to do. So I'm just going to hit the highlights here. If you have any questions, be sure and raise your hand. Of course, steel is not a modern material. It was used in ancient times, and y'all can read through that. It started wide use, or mass use in the 1700s. That picture on the bottom right is the Crystal Palace, which is a very famous structure. And then, of course, the Eiffel Tower was done in the 1889. With the Bessemer process, that's what made it start being widely used as far as structure. It's one, and then it talks about the modern use. And then it gets into the materials, what's in steel, and the differences between the different types. You got cast iron, wrought iron, and steel. Cast iron typically is 2 to 4% carbon. Wrought iron has little or no carbon. Strong in tension, but weak in compression. It's easily shaped. Any of you ever seen like cast iron furniture in a yard with the little curly cues and stuff? Or wrought iron, I think that's typically what it is. And that's because it's easily shaped, but it is not very strong. You'd think you could just beat it with a baseball bat and it'd be fine, but we had some, and in a move it just crumbled because of the weight that the movers stacked on top of it. So it looks strong, but it's not. And then there's steel, which is less than 2% carbon, strong in both tension and compression. You understand the difference between tension and compression? Tension pulls something, compression presses it. The reason steel and concrete work well together is because concrete is very strong in compression and steel is very strong in tension. So together they make a very strong unit, and that's why we reinforce concrete with steel. Talks about other alloys and things in steel. Talks about how the process of how it's made. And a little chart that shows, like a steel plant. I'm not going to read through all of that. Y'all should have already read, or if you haven't, be sure and read through all these slides. I'm just going to find the parts that are architecturally interesting. That's just a picture of a steel plant. There's piles of steel like they would pile lumber, piles of steel materials. Then how they cast it, the process. Okay, this is important. It's the shapes, and as you work through architecture or structures, you're going to learn more and more about these different steel shapes. The wide flange, or a W shape, is the most commonly used for beams. It's not an I-beam. It's a wide flanged beam. Channels are, and these are the shapes. You can see that they begin with a W. 10 by 30. We'll get into what those mean in a minute. But what they're showing you here is the black part is a 10 by 12, and the white, that's how much bigger a W10 by 30 is that outline of the white part. And here, like a 10 by 33, and then this is a 10 by 112. So then you got channels. You can remember that because it's like a C shape. You got angles, and that's C shapes have a C in front of them. Angles have an L in front of them. And then you got T shapes, which are really these up here cut in half. So it's a WT because it's made from a W, and but it's a structural T. So you need to be familiar with those kinds of shapes. And then you also got these over here. You got bars that are square, bars that are round. You got rectangles, and plates, which are solid steel. Might be a 1/2 inch thick by 12 inch by 12 inch plate. So here's the nomenclature for what the numbers mean. W, of course, is the wide flange shape. 10, it's nominally 10 inches deep. So this shape is nominally, meaning, it's not exactly that, but that's what they call it. 10 inches deep. So that is, from top to bottom, is roughly 10 inches. The 30 or the 12 means it's 10 pounds per linear foot. So if you have a beam that's a foot long, it's going to weigh 10 pounds. If it's 2 feet long, how much is it going to weigh? 20 pounds, because it's 10 pounds per linear foot. And they're all 10 inches deep. So you can see why the W30, which weighs 30 pounds per linear foot, is fatter, because you can see the outline of it, than the W10 by 12, which only weighs 12 pounds per linear foot, because it has more steel in it. Correct? So that's what you need to remember on those. And then it talks about the roller sizes, spacing, and variety of shapes and weights can be produced all nominally 10 inches deep, and it shows the exact dimensions here. And in the Manual of Steel Construction, if you're ever drawing details, which we're doing in a later class of mine, you need to know these dimensions so that you can draw the details correctly, because every inch counts when you're trying to fit a beam up in a ceiling, and you need to know where everything else goes, and you have to be able to draw the correct dimensions. Here's a picture of some wide flanges coming together, how they're connected, how they intersect. Here's a picture what I was talking about from the steel manual. The steel manual is about that thick, and this is just a page from it. But it has a legend, and you're probably going to have to look up some of these for some of your problems. And I think there's pages in the book from it. But you can see, it tells you, talks about all these dimensions here, and you can see where those apply up here. So, just on the top line, the W12 by 336 has an area of 98.8 square inches. It is the little d is 16.82 inches, or 16 7/8. I can't read that very well, but I think that's what that means. So from there to there is 16.82. The TW, which is right here, I think, it's really unclear, that picture, or maybe it's this one right here. I think it's that one. Is 1.75. The width, BY, this dimension here, is 13.385. The thickness, TF, or maybe that's TF right there. You can probably see it better in your book. But you see how that corresponds. So if somebody says, draw me one of those, you can look in your steel manual and you can know exactly how to draw it, because all the dimensions are right there. There's some other shapes. The S18, the S shapes are standard shapes. They're similar to the W shapes, but you can see they're a little bit different. They're more slender. Yeah, you can remember the S that way. The M is a miscellaneous channel, and then American Standard channels, so forth. So it's talking about. Let me go back here. How do you tell? It's talking about the numbers here on how do you tell what they are. So like a S18 by 70 is 18 inches deep, 70 pounds per foot. So just like the W's, the channels, 10 inches deep, 33.6 pounds per foot, 6 inches deep, 13 pounds per foot. So it's the depth and the weight per foot, linear foot. And the angles are a little different. You got a L4 by 3 by 3/8, so that means the Nominal leg lengths are 4 inches right there and 3 inches. And then the thickness, from that side to side is going to be 3/8 of an inch. A structural T, nominal depth is 13.5, and it's 40, so it's the same as the others, 47 pounds per foot. Then it talks about the alloys again and stuff like that. Weathering steel, a lot of times once steel develops a layer of rust, that actually makes it stronger. So you might see old bridges with rust on them, but they're really, they're meant to be that way because that protects them and it makes the material stronger. Stainless steel, of course, has a alloy in it that keeps it from rusting, and you use that on when you don't want rust to, like on docks and things, you don't want that to eat through your nails and your bolts. Cold form steel is what we use, like that looks like a decking material. This is a corrugated steel decking, it says, and it's it's a sheet, and then it's formed into these shapes, and then you would pour concrete on it, and it makes a steel concrete deck. You can also make steel studs and joists, which we'll get into later. Here's some tubes, hollow structural sections. You'll use those for columns sometimes. And here it talks about the designation, 8 by 8 by 1/2. So it's 8 inch by 8 inch nominal size, and the wall thickness, that part right there is going to be a 1/2 inch thick. Then there's joist, just like with wood. You got open web steel joist, which are much stronger and lighter than the same if you just had a solid steel member. So that's why we use those, because it's much more efficient. And you can run, wires and ductwork a lot of times through those openings in the joist and have a smaller ceiling space. Riveting is how they used to put it together with rivets, but that's not used as much anymore. Nowadays we use more welding and bolting. It's welded usually in the shop. Sometimes it's field welded, but most times I think they try to do most of the welding in the shop where they can control the circumstances, and then in the field they will bolt what's left that needs to be bolted together. Here's some bolts. They're talking about different types of bolts and what you might need them for. Another thing to remember, I think it talks about somewhere in here, is using the same type steel. I'm sure we'll get to it, so I won't belabor that, but if you're using stainless steel, you want to use stainless steel connectors. If you're using, because different types of steel will tend to corrode each other if they're touching. So talks about the connection here, slip critical connection. You don't want these to slip past each other, so you have to have a bolt that is tensioned to such an extent that the movement between the members is resisted by the friction. And all of this, generally is decided by the engineer, but you just need to be familiar with these terms as an architect so that you can have an intelligent conversation. Turn of the nut method is a way they use it. See these little bumps? Once those get flat, you've tightened it enough. That's a load indicator washer. They also have, these other types, tension control bolts. Then they talk about welding. There's lots of different types of welds that, if you do become an architect, you need to be very familiar with those. It's on your exam, your structures exam, but it talks about the different terminologies. There's the arc, the slag is what they put in there, puddle of molten metal, direction of the electrode travel. It's all too scientific for me. But this is what architects need to know, is the shapes of and why you would use different welds. You got the V groove weld, which is obvious because it's a V. You got the V bevel. You got the fillet weld, which makes a fillet. You got the double bevel. You got the double fillet. You got the puddle weld, looks like a puddle, and so forth. And these are the weld symbols, and we're studying this. These are one of my other classes on how you draw these and what the different symbols mean, because they all have a significance to the welder, so they know exactly how to do the weld. I'm not sure. Do I want to watch this? Let's see what this is. Might be interesting. Oop, it's not available anymore. Okay. Need to take that slide out. Okay. Details of steel framing. Here's where you can draw me stuff to get extra credit, so that you understand how steel frames are put together. This, of course, is a bolted connection. You have angles. There's holes pre-drilled into the beams, and then you bolt these angles on there. You slide this in there, and it goes in that little groove, and then you bolt them on. That's one way to do it. Shear talks about shear connection transfers to the gravity load from the beam to the columns, but the connection is not sufficiently rigid to transfer bending forces. We talk about shear and bending forces. Shear is the tendency for something to slip past each other. Like this is a shear connection, because this, if there's enough weight put on it, this will just break off and slide down. Bending would just cause it to rotate or bend. And when you design different connections for different forces that joint is going to withstand. So they're saying that here the transfer shear just transfers gravity loads from beam to column, but the connection is not rigid, meaning it's not stiff enough to transfer bending forces. So this could possibly twist and deform somehow if it doesn't have another type of connection or part of it that would keep it from bending. These are shear tabs right here. They're welded to the column and then bolted to these beams. Here they talk more about the moment connection, and the way they are doing this is the web of the beam. This is the web, the inside part, is connected to the column with the bolted angles. So there's your shear connection, just like we saw before. And then the top flange, the top part is called the flange, and the bottom flange, are field welded with full penetration. You can see they've shown the dark part as a weld. And that keeps it from rotating or twisting. So now this one is protected against moment and shear. Or bending. Bending is moment. They talk about other connections, the dog bone. Here's a pair of column with moment connections, because you can see how it's welded on the flanges. You can see the welds. When we design buildings, we need to have them stable against wind, against earthquake, against gravity, and whatever trucks running into them, whatever. So this is just a simple picture of how the rectangular geometry of the building frame must be stable. And so to prevent this from happening, you're going to need diagonal bracing. Why is that rotating? So they put these diagonal braces in the building, and that's the same as in our wood construction. Remember, we put sheathing on the walls, the plywood sheathing. In a steel structure, you put these diagonal bracings. That does the same thing as the plywood sheathing. It keeps that face of the building rigid so that it won't sway one side or the other. The difference between diagonal bracing and eccentric bracing is you can see that the diagonal meets and the eccentric doesn't quite meet there. It's just a little bit different. You can also have a very stiff frame, a moment resisting frame, where all of these connections are welded and bolted so that they're all just extremely stiff, and then that's a way to resist the see, these connections aren't as stiff by the way they've shown those. These are all just solid, so they won't go anywhere. But that's probably more expensive. I don't see that done as much. Here to talk about a shear wall, you can just make a solid panel. That does the same thing. A lot of times in buildings, you'll have what's called the core in high-rise buildings, and and that's usually where the elevator is, and in the middle, the inside, that's going to be your shear component for that building, because it's all solid walls. You might notice that, every tall building has that. Here's some more type of bracing. Here they're showing some rebar coming out of the concrete. More beam connections. Here's an end, what they call an end plate. You can see it in diagram and then real. Beam to girder. A girder is typically bigger than a beam, so this would be your girder, and then your beams are going to lock into that. And they have to be coped, which is that term right there, where they cut them down so that the top of these, because you're probably going to have a floor on top of this, so you don't want a big bump in your floor, so the top of these beams have to be at the same level as the top of the girder. Sometimes you need to splice beams, and that doesn't make them any less strong, but you just have to do it right. For instance, if you're going up in a high-rise building, you might not need the same size beam on the fourth floor as you do on the first floor, because you're not holding up as much weight. So here they've got a stronger column in this case, and then they're going to shift down to a thinner column. So they have some filler material, and then it's all bolted together. You can see one in real life. There's another way to do it. You can put a plate on top, and then the angles. Like I said, y'all can read through all that. So when you frame with steel, it's similar to what you do with wood. You're looking down. This is a plan view. You're looking down on this right now. And these, you're cutting through your columns. So all these W shapes are your columns in the building. Then you're going to have some girders probably on the outside, and these are probably girders here. And then you're going to have beams supporting your floor. And your engineer, or out of that AISC manual, will tell you, how much these items can carry based on the weight of your building, what's going to be in there, the loads, and then they'll decide what size that needs to be. So, and how far apart these need to be. So we've got a W at 27, which means it's 27 inches deep, and it's 102 pounds per linear foot. So that's a heavy girder. I would call that a girder that goes around the outside. And then you got your beams, W18, it's only 18 inches deep, 40 pounds per foot. And then this one's a little bit heavier because it goes from column to column. So that's how that would be a floor framing plan on a beam, on a building. This is a drawing you might see from the shop. There's several stages. The architect designs the building, then the engineer designs the structure, and then once it starts to be built, you get shop drawings. And so here's and those are more detailed. Whoever's manufacturing the steel pieces will draw them up first, and then they'll send them back to the engineer and the architect to make sure that that is what we want, and that all of these connections, the holes that are going to be drilled, are all in the correct place, because once you get it out to the field, you don't want to have to drill a hole in a piece of steel that's 2 inches thick. So this is what a shop drawing would probably look like that came from the fabricator, and then they would send it back with any corrections, and then it would be built. There's a very complicated connection. Here's a picture of them welding. So one thing you got to do, when the steel comes to the site, it's all labeled like this. And the architect and engineer, once the steel is delivered, have to go out and check their drawings, check the shop drawings, and make sure all the pieces are there. It's basically counting all the pieces. So that's a pretty boring job. I've done that. It's something that has to be done, because if something's missing, you want to catch it now rather than later. The erector is the person that puts the steel together on the job. Here they're using, remember we saw that corrugated decking, cold formed steel before. This is what that is. They're putting that, laying that down, and they're welding it to the little studs that are sticking up here. And that will help bind it to the concrete that's going to be poured on top of it. Here's some examples of floor and roof decking. These ribs make it stronger, and you don't obviously need as much concrete because the concrete won't go down there. So it's a lighter, stronger, once the two elements are bonded together, the concrete and the steel, makes a very strong deck. Plus, this allows you, again, to run electrical or small plumbing pipes in those little ridges. Here's the shear studs. You can see this is a detail showing your beam with the studs. These are the studs coming out of that little beam, running right here. Then you can see that line right there is the bottom of the steel deck. Then it comes up and you have this line, so you're cutting through it and you see that line right there, and then your concrete is going to go another probably 2 inches on top of that. So you have a 4-inch concrete deck overall. So that's what that detail would look like of how that's formed. Here they're pouring the concrete. They also, in this case, have a welded wire mesh that also reinforces the concrete. And here you can see here they have some precast panels and precast floor panels on this one. So you think that steel is fireproof, but it's not. It melts when it gets to a certain temperature, and that's what happened, of course, to the World Trade Center when the planes hit it. That it was so hot that the steel eventually, melted and the buildings collapsed. It couldn't hold itself up anymore. So, especially since then, but even a little bit before then, you have to fireproof your steel and try to make it stand as long as possible in the event of a fire, to give everybody in there enough time to get out before it collapses. So you have to make sure that it's fireproofed. And you can do that with concrete. You can surround your steel in concrete or plaster, gypsum wallboard. There's also spray insulations, different ways to do it. I don't think there's a column. See that in the back corner there is a column, and that's covered. It probably looks kind of like this detail here. It's got gypsum wallboard all around it, so that it just fits in with the wall, basically. That's how it's normally done in, small office type buildings. Here you can see some fireproofing that has been sprayed on to the ceiling. And then they're spraying some in here on these things as well before they cover it up. There's some more fireproofing. Notice that the cross bracing does not have to be fire protected, because it doesn't. That protects against wind and shear loads like earthquakes and wind loads, not gravity loads. You want the fire protection on gravity loads so that it doesn't collapse and fall down. So if these melted, the building would not fall down. That's what they're saying. But if these columns melted, of course the building would fall down. That's the end of that. Okay. So this copy machine, I messed up making the copies, but let's see. Pages aren't exactly in order. so this, and you can work together on this. You got this front page, which there's really no information. Then you should read this page. Then you got that page, and then you got that page. So it's kind of like backwards. But the instructions, it says, this exercise will familiarize you with the dimensional properties of steel structural shapes. You will need to refer to figures 11.12 and 11.13 of the text, keeping in mind that you are looking here at only a small sampling of the available steel members. Wide flange shapes, for example, are available in depths ranging from 4 to 36 inches, although the relative proportions of the shapes are more or less constant regardless of size. Figure 11.12 is divided vertically into two parts. The second part gives you structural properties of the shapes that will be familiar to those of you who have studied structural engineering. All of the information you need to complete this exercise is contained in the first part. You will see that the cross-sectional area of each shape is given, along with its actual depth and the detailed dimensions of its flanges and web. The distance capital T, little k, and K1 are particularly useful. They locate the point at which the curved fillet begins between the flange and the web. T is also maximum length of the plate or angle that can be fastened. All that's in that chart that's on that those numbers are referring to. Notice that each group of shapes in the table shares the same nominal flange width and nominal overall depth. T is constant within each grouping because of the same blah, blah, blah. Let's see. The shapes for the 12-inch and the 10-inch flange widths are used largely for columns, while other nominal sizes of relative narrow flanges used primarily for beams. So then if you go to this page, the one with the center lines on it, it says draw accurate sections of the shapes indicated, each centered on the given center line with its lower edge on the solid line. So what it wants you to do, there's 3 shapes shown here, and then remember we talk about scale. Down here at the bottom it says 1 square equals 1 inch. So you can kind of see these squares, and so you're drawing this at 3 inches equals 1 foot. So that means 1 square in this page equals 1 inch. The squares you can barely see. So for it says for number 2, you know, after you draw these shapes, for a better idea of the true size of these shapes, draw your hand at the same scale. So, you know, say my hand is 6 inches long, then my hand would only go up 6 squares, and so you could draw a little hand there so you can see, you know, how big this beam is you're drawing. So let's do one of them together. Let's see if I can help you do that, and then you can do the others. Show a grid. So on here, my little grid, my squares will be 1 inch equals 1 square equals 1 inch. What page are those tables on? 423. 422, 423. Okay. Okay. Yeah, so that's what we're looking at. These, and those are pages just like that slide I was showing you earlier, taken from the book. I mean, from the AISC manual. So it says a W12 by 22, and I've already got it highlighted in my book. It's this one down here is what we're going to be looking at. So y'all look at that. And so first I'm going to draw, just so that I can be on the same page as y'all, a center line. So the center line is going to be the center of the beam. Why is it red? Oh well. That didn't show up very well, does it? Yeah, that's better. Hold on. Okay, there's my center line. Now I'm going to go to black to draw. Get a little thinner. So you got your center line, which has that CL there. And then you also have the bottom where they want you to start. So I'm just going to draw that. That shouldn't be a center line, but that's okay. So I'll make my lines straight. So the first thing we need to see is that a W12 by 22, looking on this chart, how tall is that going to be? If you look on that chart. If you look at the picture at the top, there's a dimension with a little d. So if you, anybody got a good guess? Chart's on page 422. And you got a picture of all the little, what all these columns mean as arranged by the picture at the top of the chart. So you have a little d, which is the total depth. So is there a column there that has a little d on it? Huh? Come on, people. 12.31 or 12 1/4 inch. So if each square is 1 inch, I'm going to count up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's 12 1/4, so it's going to be just a little bit higher, you know, maybe one. That's where the top is going to be. So I'm just going to draw that roughly. So now I know that. So to me, my next dimension would probably be that how wide is it going to be? And that looks like it would be the one with the little b, BF, which is width. So if you look over and follow width down to your W12 by 22, how wide is that going to be? 4 inches. So if this is a center line, how far will it be on each side? 2 inches. So just for now, I'm going to draw, so there's 1, 2, so I know it's going to stop there, and it's probably going to stop there on that line, and then it's going to be the same thing down here. I'm just sort of drawing the outline right now, and then I can finish it up. So there's my beam is going to be contained within this, right? So now the flange, which is the middle section, and that is the TW, the web thickness. So you can see up there, there's the X, and then below it there's the TW, and then in your chart there's the web thickness. So how thick is the web going to be? On the W12 by 22. The web, TW. Right, or 1/4 inch. So that's just barely going to be on each, it's going to be 1/8 inch to each side of my center line. Of course, your lines won't be as fat as mine here, but, so, just probably as close as you can draw it almost. It's hard for me to do it this, oops, because it's going to grab to that. Let me see. Make this a little thinner. So, I can't draw good on this thing, obviously. Try it again. This line is going to be 1/8 inch or 1/8 square over on each side of that. So that's about as good as I can get it on this program. You're going to have your bottom line here, so you can go ahead and make that solid. Your top is going to be up here. So you can, why isn't that erasing? Huh. Erase. No. Well, sorry. Moving on. You're going to have a line here. Okay, and you got your bottom here. And then the next thing you want to know is the TF. which is the flange. I termed that wrong. This is the web thickness right here, and up here you got your flange thickness, and that's the same on the top and the bottom. And on that, so up here on your chart it says TF flange thickness. So how thick is that going to be on your W? 0.425 or 7/16. So just draw your best guess at that. That's almost a half an inch. So, probably somewhere down in here. And then it's going to be the same. If these squares are an inch, it's going to be about like that. So then the only other question is, so that's roughly the shape of your W12 by 22. So now you need to do the same thing for these other shapes, a W12 by 35, and down here they've got two shapes, a W12 by 65, and then they want you to overlay a W12 by 336. Because remember, it's probably going to be a lot fatter because it weighs more per linear foot. So you can see the difference when you scale that out. So you're going to finish that, and then on this other sheet, this page with the square on it, don't worry about number 4. I just want you to draw the sections of the angles based on, I think you can find that information on this other chart on page 423. So y'all can work together doing that, and then that'll be what's due. And next time we'll go over chapter 12 and any questions you have for the review.